Hi and welcome to Jawad's Academy. Today's lesson is about types of asymptotes. When we're dealing with types of asymptotes, we must consider when we are graphing a rational function. Asymptotes are restrictions on a graph of any rational function, just like domain and range. We have three types of asymptotes to consider when we're dealing with rational functions: vertical asymptote, horizontal asymptote, and oblique asymptote. But we cannot have both horizontal and oblique asymptote at the same time. We can have vertical asymptote and horizontal asymptote. We can have vertical and oblique asymptote, but not all three at the same time. And I'll show you how to find vertical asymptote. Vertical asymptote is a restrictions in the denominator of a rational function, where we cannot have 0 in the bottom. For example, if I have f of x equals 2 over x minus 1, and you can see clearly your restriction is x cannot be 1, because the bottom will equal to 0 if you were to substitute for x 1. So vertical asymptote is, in this case, x equal to 1. So the vertical asymptotes comes from the zeros of the bottom of a rational function. So if you have a rational function, once you find the zeros of the bottom, that is your vertical asymptote, and that's also your restriction, your domain. Now about horizontal asymptote. When can we have a horizontal asymptote? Please hear me and write it down, because this is very important concept. How to determine horizontal asymptote from a rational function. So if the degree of top and bottom of a rational function are equal, the highest degree, then we divide their coefficient. That is your horizontal asymptote. Example, f of x equals 2x squared plus x minus 1 over x squared plus, for example, 5. Now you can see that the degree of top and bottom are equal, the highest degree, which both are quadratic relation. Then how to determine the horizontal asymptote? We're just going to divide their coefficient. 2 divided by 1, which equals to 2. That is your horizontal asymptote. The easiest way to find the horizontal asymptote. You just divide their coefficient. And there's other condition also that we can have a horizontal asymptote when we're dealing with rational function. If the higher degree is in the bottom, not on top. For example, f of x equals 2 plus x over x squared minus 9. Now you can see the degree is higher in the bottom. So your horizontal asymptote would be automatically 0. Because, and you were wondering why is it 0? 100%, yeah, it's a valid question, and I like to show you, and I love to show you why. Because math works with the reasoning. So remember this. Now I have 2 plus x. Now I'm going to rearrange this, and I'm going to write as 0x squared plus x plus 2. Still means that it's x plus 2. So I'm not changing anything to top. I'm just rewriting it as 0x squared plus x plus 2. Like there is no x squared. So I'm just going to write coefficient of x squared as 0. Still means we have x plus 2. And in the bottom I have x squared minus 9. Now since I have the degrees are equal, top and bottom, then I'm going to divide their coefficient. 0 divided by 1, which equal to 0. And there's also another way to determine the horizontal asymptote would equal to 0, when you can do as limit of x approaches infinity. This is another way to find horizontal asymptote. As limit of x approaches infinity, I'm just going to push it up in order to get space. So let me write the same example. As x approaches infinity, in order to evaluate this, we'll get our horizontal asymptote. We have x plus 2 over x squared minus 9. Now to find or evaluate this limit, the definition of limit of x approaches infinity is you divide every single term the highest degree of the bottom, which is in this case x squared. So that means as limit of x approaches infinity, we divide x squared by x squared 9 by x squared, and x over x squared, and plus 2 over x squared. So we divide each of these terms by the highest degree of the bottom, which is x squared. Then we reduce before we substitute for x infinity. So in order to reduce, we will have, again, as limit of x approaches infinity, we have x over x squared, which is 1 over x. If we were to reduce, then we cannot reduce the second term. We leave it as 2 over x squared. Here we can reduce, the degrees are equal, so be 1 minus 9 over x squared. Now we're ready, after reducing, make sure to reduce before you substitute for x infinity. Now we're ready to substitute for x infinity in order to evaluate, find our horizontal asymptote. So be 1 over x. When you substitute for x infinity, it will approach 0. Plus 2 over infinity, also it approaches 0. 1 here, subtract 9 over infinity will be 0. So on top we have 0, and in the bottom we have 1. So you can see that therefore the horizontal asymptote is 0 divided by 1 is 0. That's another way to find the horizontal asymptote. But I would suggest to just go by definition. If the degree is higher in the bottom than the top of a rational function, it's automatically 0. And there you go. Very easy to remember. And this was just a proof of it. Sounds good? Now we go into our third asymptote, types of asymptote, which is oblique asymptote. When can we have oblique asymptote? Please write it down. Very important concept. When the degree is higher on top this time, then you can have oblique asymptote. Right? So let me show you an example of oblique asymptote. F of x equals, for example, x squared minus x minus 1 divided by x subtract 1. Now clearly you can see this rational function has a higher degree on top than the bottom. So we have a quadratic and we have a linear in the bottom. Now to obtain your oblique asymptote, you have only one way to do it, which is long division. Absolutely. Because oblique asymptote is the equation of a line. It's in terms of y equals mx plus b. So it's a slanted kind of asymptote. It's not vertical. It's not horizontal. It's like y equals mx plus the equation of a line. It's slanted diagonally. So in order to determine the oblique asymptote, we perform long division. So we write our long division. Divisor goes right here. Your dividend goes here, and you perform long division. If you forgot long division, no worries. I did do a lesson on long division and syntactic division, so you can go ahead and watch those, and I'm sure brings back the memory, and you should be able to understand what I'm doing here. So x squared divided by x would be x, and then you multiply and multiply. So x times x is x squared, negative 1 times x is negative x, and then we subtract. This would be 0, that would be 0. We bring this last term down, which is negative 1. Now we can no longer divide negative 1 by x because the degree of remainder is lower than the divisor, so we cannot divide. It has to be either equal or higher in order to divide. So our equation of the asymptote would be, oblique asymptote is y equals x. Has to be equation of a line, like we said. So these are three different types of asymptotes. And I can show you how they look like on a graph, kinda. I'm sure you know your vertical and horizontal, how does it look? And then also I'm going to show you the oblique asymptote. Vertical asymptote crosses the x-axis, whatever the value of x is, anywhere. That's your vertical asymptote. Horizontal asymptote crosses the y-axis, anywhere on the y-axis, horizontally, as long as you have the value of your horizontal asymptote. Oblique asymptote is equation of a line, y equals mx plus b. In this case, it's y equals x. So you draw your equation of a line this way. That's your oblique asymptote. Or could be also sometimes going this way. Sounds good? These are your asymptotes. This is how they look like. And I'm hoping that you understood about these types of asymptotes. and how to determine these types of asymptotes from given rational functions. So I'm going to stop right here our lesson. Please don't forget to subscribe, thumbs up, and I would really appreciate if you have a question or a comment, leave it on and below in comment box, and I'll be able to reply back. Till next time, take care and wish you all the best.